Deadlock as an important topic in operating system. So deadlock is one of the important concept in operating system, and you may expect most of the questions from deadlock topic. So let us see about deadlock and the problems, practice problems which is frequently asked in the deadlock topic. Okay, so deadlock. So what is mean by deadlock? First understand the concept, then because most of the questions are based on the theory also, not on problem, because it is a concept side, concept oriented subject. So you may expect most of the questions like theory questions also. So you need to more focus on understanding the concepts of operating system. Let us see the definition of operating system. Okay, so deadlock is a situation where the execution of two or more processes is blocked because each process holds some resources and wait for the another resources held by some other process. As you can see in the picture, we have two processes P1 and P2, and we have two resources R1 and R2. And the process P1 is in need of resource R2, but unfortunately the resource R2 is held by process P2. The process P2 additionally requires R1, but this resource is already used by P1. So no processes would fulfill their resources. So still all these processes are in waiting state. No process will complete the work. So this situation is what we call as deadlock. Okay, the execution of two or more processes is blocked because each process holding the resources and wait for the other resources, but which is held by some other process. Okay, so here as I said earlier, we have two processes. Process P1 holds resource R1 and wait for resource R2, which is held by process P2. Process P2 holds resources R2 and waits for the resource R1 to complete, but it is held by process P1. Okay, none of the two processes can complete and release their resources. So this both the process keep waiting indefinitely. Okay, this is the basic concepts of a deadlock. Okay, what are the conditions for deadlock? What are the conditions that make you in a deadlock situation? There are four conditions. One is mutual exclusion, hold and wait, no preemption, circular wait. Let us see in detail about all these four conditions. First one is mutual exclusion. By this condition, there must be exist at least one resources in the system which can be used by only one process at a time. So we have one resources, that resources can be used by one process at a time. That resources cannot be shared by other process. Okay, and if there exists no such resources, then deadlock will never occur. If there is no such resources, okay, then deadlock will never occur. And say for example, we have a printer is a resources. Okay, so printer is an example of a resource that can be used by only one process at a time. We cannot take more than one printout at the same time. Only one paper at a time you can insert into the printer device, and then it will take next printout. Okay, so we have a shared resource printer, but one process can at a time can use the printer resources. So this is what we call as mutual exclusion. If other process wants the printer, then the second process has to wait until the first process use the printer. Okay, this is the mutual exclusion condition. The second one is hold and wait. By this condition, there must be exist a process which holds some resources and wait for another resources held by some other process. So this hold and wait is nothing but there is a process which is having some resource. Okay, but it needs to wait for another resources, but that resources will be held by some other process. So this will create a deadlock situation. No preemption. By this condition, once the resources has been allocated to the process, it cannot be preempted. Okay, say for example, there is a process using one resources. Okay, the second process wants that resources from P1. It wants the resources. Okay, in the middle of the usage of that resources, you cannot be preempted. You cannot force the process one to release the resources. Okay, so that is the no preemption. You cannot preempt, you cannot forcefully take the resources from the process which is right now using it. Okay, once the resource has been allocated to the process, it will not release it unless it finish the process. It cannot be preempted. So it means the resource cannot be snatched forcefully from one process and given to the other process. So this process must release the resources voluntarily by itself. Once the process made use of the resources, the process itself has to release it. Okay, that is no preemption. If you follow this no preemption, no deadlock condition will occur. Okay, and I'll repeat. The first one is mutual exclusion. Okay, second one is hold and wait. Third one is no preemption. Fourth one is circular wait. So by this condition, all process must wait for the resources in a cyclic manner, where the last process waits for the resources held by the first process. As you can see, the process P1 is wants some resources, but it is held by process P2. Process P2 wants some resources, but it is held by process P3, and P3 wants some resources, but it is held by P4, and P4 wants resources, but it is held by P1. So it is in a cyclic manner. All the process is waiting for a resources. Okay. So if this manner continues, no process will complete their work. Okay, all the process will be waited infinitely. Okay, and what are the important note we have to take in from these four conditions? So all these four conditions must hold simultaneously for the occurrence of deadlock, and if any of the condition fail, then the system can be ensured deadlock free. So you need to make sure that all these conditions should not be entered. Okay, when you allocate resources to the process. Okay. Okay, how to handle all this deadlock situation? Okay, we need to ensure that there will not be any deadlock when you allocate resources to the process. I want to recall what is resources. Resources are nothing but it may be a printer, memory, if any process wants to execute, what are the things we require to store a program? We need a memory. So memory is one kind of a resources, and a CPU, because a process wants to execute by the CPU, so CPU is also one of a resource. Okay, and these are all what we call as resources. Okay, and because CPU can execute in the way of process, the execution of process requires many resources. The allocation of resources may create this deadlock situation. Okay, so come back to the strategies of handling deadlock here. So deadlock handling strategies are deadlock prevention, deadlock avoidance, deduction and recovery, deadlock ignorance. Okay, so let's see one by one. Deadlock prevention. Okay, so this strategy involves designing a system that violates one of the four necessary conditions that makes the occurrence of deadlock. Okay, as we saw earlier, we have four conditions that will create a deadlock: mutual exclusion, hold and wait, and then circular wait, and no preemption. If so, we need to ensure that these conditions should not enter. Okay, so that deadlock will not occur. Okay, so let's see how this deadlock will prevent not to enter those four conditions. So the various conditions of deadlock occurrence may be violated as: the first one is mutual exclusion. To violate this condition, all the system resources must be such that they can be used in a shareable mode. Okay, so the first thing is mutual exclusion, in the sense what the one resource is there, that resource can be taken by one process at a time. You cannot share the resources, like two processes never share the same resources. Okay, so if you want to share a resources, then the process has to wait. Okay, say for example process 1 using resource R1, but at the same time the same resources can be required by P2. The P2 has to wait until the P1 releases the R1. Okay, so to violate this condition, all the system resources must be used in a shareable mode. So in a system, there are always some resources which are mutually exclusive by nature. So this condition cannot be violated. Next one is hold and wait. So this condition can be violated in the following ways. The first one, approach 1. We have several approaches to violate this hold and wait. A process has to first request for all the resources it requires for execution. See, initially, say for example, we have three process 1, process 2, process 3. Okay, all the process makes a request of all the resources that is required for an execution. Say P1 wants printer. Process P2 wants CPU and memory, and process P3 wants again CPU. So you need to initiate what are all the request the process wants before it starts an execution. For an execution, what are all the resources required by the process? Okay, so once it has acquired all the resources, only then it can start its execution. Okay, it's like initially you need to take all the resources, process 1, process 2, process 3. You need to take all the resources. Once all the resources has been allocated to the particular process, then it has to start execution. Okay, while execution itself, it never asks for resources. Before starts an execution, every process has its own resources. Okay, that is the first approach. So this approach will ensure that the process does not hold some resources and wait for the other resources, because initially all the process got all the resources, so there will not be a chances of occurring a deadlock, right? So this is the approach 1. But what will be the drawback? It's very easy and you can able to understand. There is no chances of entering deadlock situation because every process has its own resources. But the drawback here is it is less efficient, it is not implementable, since it is not possible to predict in advance which resources will be required during execution. So it is obviously during execution only some process may know the requirement of resources. We cannot predict initially what are all the resources that we want. Okay, sometimes some process may want input device, some process may want output device, some process may not want input device and output device. So it is very difficult to predict initially what are all the resources that we want. Input and output devices also and resources. So that is the less efficient approach. Okay, but deadlock never occur when we go for this approach, but it is not at all possible to predict in advance in which resources will be required during an execution. Okay, what is next approach in hold and wait? In this approach, a process is allocated to acquire the resources it desires at the current moment. Okay, after the acquiring the resources, it starts its execution. Now, before making any request, it has to compulsorily release all the resources that it holds currently, and this approach is efficient and implementable. So the concept here is like right now I want input device, I don't want printer. See a process, say for example I have a process. Okay, this process requires various resources, like I want the process want input device, output device and input device, output device and CPU. These three resources this process want. See, when we are going to take the output device, at last only we require output device to display the output, right? Or to take a printout. So currently what resources the process is required? Input device and CPU for execution. Okay, so that kind of resources I can acquire at that moment, and once I want output device, that time whatever resources that a process have, that has to be released. Okay, that is the concept of approach 2. So it is somewhat efficient. Instead of getting all the resources with you and making the resources to idle, instead of making use of it, you can whatever the resource which is required right now, that resources may be acquired, and when you want, release the resources which you have, and then use the required resources. Okay, so this approach is somewhat efficient compared to approach 1. The third approach is a timer is set after the process acquires any resources. After the timer expires, a process has to compulsorily release the resources. Okay, and I think you can easily understand. We have a timer for every process. It's like you may aware that we have a round robin fashion, right? Like for every 2 seconds, we have to preempt the resources. Okay, every process have some resources, but for particular period of time only the process will make use of the resources. After the time expire, all the process should be release the resources. So that is the concept of this approach 3. So if we follow approach 1, approach 2, approach 3, sure, we can prevent the deadlock situation. Okay, the next one is a non-preemption. Okay, the third condition, how we can violate this non-preemption. So this condition can be violated by forceful preemption. Consider a process is holding some resources and request other resources that cannot be immediately allocated to it. Okay, consider we have a process holding some resources and request other resources that cannot be immediately allocated it. So then by forcefully preempting the currently held resources, that conditions can be violated. See, we have a process and it is possessing some resources, but the resource is not at all used at that time by that process. So that time you can forcefully preempt, you can forcefully take in the resources from the process. That is the non-preemption concept. Non-preemption in the sense you should not preempt, you should not forcefully ask the resources to release. Okay, so but if that resource is idle by that process, that time we can take the resource from that process. Okay, if there is no use of that process but still the process is holding, then other process can preempt it. Okay, so a process is allowed to forcefully preempt the resources possessed by some other process only if it is a high priority process or a system process. We have many different types of processes are there, user process, system process are there. So only if it is in a high priority process, system process, you can preempt resources, and the victim process is in waiting state. Okay. Yes, circular wait. So let's see what approach we are following for this circular wait condition. So this condition can be violated by not allowing the process to wait for the resources in a cyclic manner. So to violate this condition, the following approach is followed. The first approach, a natural number is assigned to every resources. Each process is allowed to request for the resource either in only increasing or only decreasing order of the resource number. So each process is allowed to request for the resource either in increasing order or decreasing order of the resource number. Based upon the resource number, either you can call in increasing order or decreasing order. So in case increasing order is followed, if a process requires a lesser number resource, then it must release all the resources having larger number, and vice versa. So this approach is the most practical approach and implementable. So when you follow this number order, cyclic formation is not at all followed. So however, the approach may cause starvation, but will never lead to deadlock. So starvation in the sense it will make you wait for a longer time, but instead of doing nothing, you can wait for acquiring the resources. So this is the approach following for circular wait. Okay, the second way of handling deadlock is deadlock avoidance. So as of what we saw is how we can prevent the deadlock. We need to violate all these 4 conditions. Violating any one of these conditions cannot occur the deadlock situation. Okay, next one is deadlock avoidance. So this strategy involves maintaining a set of data using which a decision is made whether to entertain the new request or not. So we are following one strategy whether to make a new request of getting resources or not. Okay, if entertaining the new request causes the system to move in an unsafe state or safe state. If it is an unsafe state, then it is discarded. Okay, say if a process requesting for some resources, when we allocate resources to the requested process, and you need to check whether it is safe to allocate it or not. Okay, if it is safe, then you can allocate it. If it is unsafe, then it is discarded. So this strategy requires that every process declare its maximum requirement of each resource type in the beginning itself, because you are checking whether allocating resources to your particular process is safe or unsafe. Okay, how we can determine whether it is safer or unsafe? So we need to get a declaration of every process, how many resources they want. Okay, so that strategy we are following here. Okay, so this strategy requires every process declares its maximum requirement of each resource type in the beginning. We have many different types of resource type. As I said, input device we have an output device. Output device we have a monitor is one of the resources, and printer is one of the resources, scanner. So, and then these are all the different types of resources are there. So every process has to declare how many, that is maximum requirement of resources they want. And main challenge with this approach is predicting the requirement of the process before execution. As we discussed earlier, a prediction of requirement is somewhat difficult, but we can avoid deadlock by doing this. And the good example of following this strategy is Banker's algorithm. So it is an example of how deadlock avoidance strategy is used in the application. Okay. The third one is deadlock detection and recovery. We can see Banker's algorithm later, because by explaining Banker's algorithm only, you can get to know how we can avoid the deadlock. So we have some algorithms. By applying algorithms, we can avoid the deadlock. So we have data structures, and some procedures are there. Applying procedures in different problems, you can easily understand the deadlock avoidance concept. The next one is deadlock detection and recovery. So this strategy involves waiting until a deadlock occurs. So after deadlock occurs, the system state is recovered. So deadlock detection and recovery in the sense, it is waiting for deadlock to occur, and after occurring deadlock, we need to recover the system to be in safe state. So the main challenge with this approach is detecting the deadlock. So we need to check whether deadlock is occurred or not. Okay, and fourth one is deadlock ignorance. This strategy involves ignoring the concept of deadlock and assuming as if it does not exist. So it helps to avoid the extra overhead of handling deadlock. And actually this deadlock ignorance concept is used in Windows operating system and Linux, and it is most widely used method. It is also called as ostrich approach. Okay, and before we move into the problems, let us see some important concept of deadlock. Okay, so based upon this, we are going to see many problems. We are going to see problems in the deadlock, and these are all some gate questions which I have taken. Okay, so consider there are n process in the system. Let us have P1, P2, P3 until Pn. So these are all the process for execution. Okay, and where process P1 requires x1 unit of resources. See, assume resource R is nothing but we have memories. We have random access memory, read-only memory, and so many types of memory is there, right? So we require x1 unit of resource. Okay. Similarly, process P2 requires x2 units of resource R, and P3 requires x3 units of resource R, and so on till Pn. So in the worst case, the number of units that each process hold is equivalent to 1 less than its maximum demand. Okay, see, we are as I said, we have to declare the maximum demand. Okay, so the units, the number of units that each process holds, say P1 holds x1 unit, which is less than its maximum demand. Okay, in the worst case. Okay, so process 1 holds x1 minus 1 unit of resource R, and process P2 holds x2 minus 1 units of resource R. Process P3 holds x3 minus 1 units of resource R, and so on. So we had 3 mean 1 more unit of resource R in the system could be ensured deadlock free. So this is because that unit would be allocated to one of the process and it get execute and then release its units. Okay, so from here we have maximum number of units that ensures deadlock. Okay, in the worst case, maximum number of units because what we have saw is the process that hold the number of units that each process holds is equivalent to 1 less than its maximum demand in worst case. So this will create an deadlock. Okay, so maximum number of units of resource R that ensures deadlock is equals to x1 minus 1 plus x2 minus 1 plus x3 minus 1 till xn minus 1, and taking all this we will get x1 plus x2 plus x3 till xn minus n and summation of xi minus n. So which means that sum of maximum needs of all processes minus n. Okay, so maximum number of units that ensures no deadlock. This will ensure deadlock. See, if sum of maximum need of all process minus n, it means it ensures deadlock is there. Maximum number of unit that ensures no deadlock. Let's see, maximum number of units of R that ensures no deadlock. So which is equivalent to one more than maximum number of units of resource R that ensures deadlock. So summation of xi minus n plus 1. If it is more than the sum of maximum need, then there will not be a deadlock. Okay, let's start with the practice problems based on deadlock in operating system. So first problem is, the system is having 3 user processes, say P1, P2, P3. Each requires 2 units of resource R. So the minimum number of units of R such that no deadlock will occur. Okay, so the question is, there are 3 processes P1, P2, P3. Each requires 2 units of resources. The minimum number of units of R such that no deadlock will occur. So the options given here is 3, 5, 4 and 6. So let's see, the answer is 4. Let's see how they gave a solution of opting this 4 units. Okay, so in worst case, what is the formula we found? The number of units that each process holds is equals to 1 less than its maximum demand. So the process P1 holding 1 unit of resources, P2 1 unit, P3 1 unit. So thus maximum number of unit of resources R that ensures deadlock is 1 plus 1 plus 1 is equals to 3. If more than 1 means minimum number of units of resources R that ensures no deadlock means what? 3 plus 1 is equals to 4. Okay, so remember this one, we saw the concept x1 plus x2 plus, okay, this is for ensuring deadlock and this is for ensuring no deadlock. If we add one more than maximum number of units, minimum number of units of resource R that ensures no deadlock. So here the question is, a system having 3 user processes, each requires 2 units of resource R. The minimum number of units, they are asking to ensure no deadlock. The minimum number of units of R such that no deadlock will occur. Okay, so if it is maximum number, if you add all the unit 1 plus 1 plus 1, you will get 3. Okay, if it is minimum number, then you will get 3 plus 1. Already we have maximum 3 plus 1 which is equals to 4. Okay, let's move on to the second. The system is having 10 user processes from P1 to P10. Each require 3 units of resource R. The minimum number of units of R, minimum number of units of R such that no deadlock will occur. So the number of units that each process holds is equals to 1 less than its maximum demand. If it is means a deadlock. So P1 holds 2 units of resource and process P2 holds 2 units of resource P3 and till P10 holds 2 units of resource R. Okay, assume it is not 3 units, it's 3 units. So maximum number of units of resources means what? 10 into 2. From P1 to P2, 10 into 2, 20. And if you add 20 plus 1, then you will get 21. So no deadlock will occur in 21 units. So we require 21 units. They are asking how many number of units we want for 10 process. Okay. So third problem, a system is having 3 user processes P1, P2 and P3, where P1 requires 2 units of resources, P2 requires 3 units of resources and P3 requires 4 units of resources R. The minimum number of units of R that ensures no deadlock. So it's very easy. Let's see the solution. So 1 plus 2 plus 3 is equals to 6. And minimum number of units add 6 plus 1, which is equivalent to 7. Okay, the next one, a system is having 3 user processes P1, P2, P3, where P1 requires 21 units of resources R, P2 requires 31 units of resource R, and P3 requires 41 unit, 21, 31, 41. The minimum number of units of R that ensures no deadlock. So what will be the minimum number of units we want to execute the process 1, process 2 and process 3. So again write the number of units that each process hold is equals to 1 less than its maximum demand. Okay. That is summation of xi minus 1 xi minus n is equal n minus 1. So the process P1 holds 20 units, P2 holds 30, P3 holds 40 units of resource R. Okay, so thus maximum number of units of resource R that ensures deadlock is 20 plus 30 plus 40, so which is equals to 90, and minimum number of units R that ensures no deadlock, so 91. So if we have minimum number of these resources, no deadlock will occur. If we have maximum resource units 90, then sure there will be a deadlock. There will be a chances of occurring deadlock. So the next one is, if there are 6 units of resource R in the system, okay, 6 units, and each process in the system requires 2 units of resource R, then how many processes can be present at maximum so that no deadlock will occur? How many processes they are asking? Okay, so the number of units that each process holds, which is equivalent to 1 less than its maximum demand. So process P1 holds 1 unit, and process P2 holds 1 unit, and P3, P4, P5 and P6. Okay, so till from process P1, if each process hold 1 unit, then there will be no chances of occurring a deadlock. See, if there are 6 units of resources in the system and each process in the system requires 2 units of resources R. There are 6 units, but each process requires how many? 2 units. How many process can be present at maximum so that no deadlock will occur? Okay, so it may be every process may require 2 units, but the number of process that maximum number of process maximum present which that doesn't make deadlock is 6. From P1, P2, P3, P4, P5, P6. Each process from P1 to P5 holds 1 unit. Okay, the next problem. If there are 6 units of resource R in the system and each process in the system requires 3 units of resource R, then how many processes can be present at maximum so that deadlock will occur, so that no deadlock will occur? Okay, so P1 holds 2 units, P2 holds 2 units, P3 holds 2 units of resources. So minimum number of processes that ensure deadlock is equals to 3. Because if you minus units by 1, you will get 1 plus 1 plus 1. Okay, so maximum number of process that ensures no deadlock is 3 minus 1, which is equals to 2. Okay, the next problem is, if there are 100 units of resource R in the system and each process in the system requires 2 units of resource R, then how many processes can be present at maximum so that no deadlock will occur? The question is, we have 100 units of resource R in the system, and every process requires 2 units of resource. So how many processes can be present so that there will not be a deadlock? Okay, maximum how many processes should be present so that no deadlock will occur to utilize 100 units of resource R? Okay, again, in the worst case, the number of units that each process holds is equals to 1 less than its maximum demand. So the process P1 holds 1 unit and process P2 holds 1 unit till process P100 holds 1 unit. So the minimum number of process that ensures deadlock is 100. Number of process, they are not asking number of resources. The number of process that ensures deadlock is 100, and the maximum number of process that ensures no deadlock is 100 minus 1. If it is 100 process requires 100 units, then there will be a deadlock. At least if one resource unit is free by making use of 100 process, then there will not be a deadlock. So 100 minus 1, which is equivalent to 19. Problem 8. If there are 100 units of resource R in the system and each process in the system requires 4 units of resources R, then how many processes can be present at maximum so that no deadlock will occur? So here same question like previous one. There are 100 units of resource R in the system and each process in the system requires 4 units of resources. So how many processes can be present so that there will not be a deadlock occur? Okay, so how many process they said? 100 units. Okay, so process P1 holds 3 units, P2 until process 34 we have process P34 holds 1 unit of resource R. So minimum number of process that ensure deadlock is 34 and maximum number of process that ensures no deadlock is 34 minus 1, which is equivalent to 33. So if 33 process maximum number of process that can utilize 100 units of resources are 33. Okay, if number of process maybe one more than the minimum, then sure will get there may be a chance of getting a deadlock. Okay, so the next question is, if there are 100 units of resource R in the system and each process in the system requires 5 units of resource R, then how many processes can be present at maximum so that no deadlock will occur? So now 5 units, each process in the system requires 5 units. So in the worst case, the number of units that each process holds is equals to 1 less than its maximum demand. Okay, so here process P1, the number of units that each process holds is equivalent to 1 less than maximum demand. So in the question, each process in a system requires 5 units, right? Okay. So here we need to follow this worst case. The number of units that each process hold is 1 less than the maximum demand. The process requires 5 units, but it should be 1 less than the maximum demand. So our demand is 5, but you need to subtract it by 1 less than its maximum demand. So process P1 holds 4 units of resource R, process P2 holds 4 units, process P3 until process 25 holds 4 units of resource R. Okay, so that's minimum number of process that ensures 25. Okay, because we need to utilize 100 units, right? So 25, sure this will ensure deadlock. Maximum number of process that ensures no deadlock is 25 minus 1 is equals to 24. The next problem. A computer system has 6 tape drives with n process. 6 tape drives in the sense it's one kind of a resource, and it has 6 tape drives. A tape drive is a resource and number of resource unit is what we called as 6. Resource type is common, but number of units of resource type is 6. So the number of system has 6 tape drives with n processes competing for them. Each process needs 3 tape drives. The maximum value of n for which the system is guaranteed to be a deadlock free. Okay, a system has 6 tape drives with n process. We have process P1 to Pn. Okay, each process needs 3 tape. Availability is 6, but the need is 3 by n process. So what is the maximum value of n for which the system is guaranteed to be deadlock free? So how many process can make use of 6 tapes so that no deadlock will occur? Is that 2, 3, 4, 1? So the answer is 2. Because see, if two process needs, if there are two process, each process requires 3 tape drive, right? So there will not be a chances of creating a deadlock situation. Okay, so the number of tape drives that each process holds is 1 less than its maximum demand. So process P1 holds 2, process P2 holds 2, process P3 holds 2 tape drive. Thus minimum number of process that ensure deadlock is equal to 3. If you have 3 process, then sure deadlock will occur. But maximum number of process that ensure no deadlock is 3 minus 1, which is equivalent to 2. So 2 process. Okay. Okay. Consider a system having m resources of the same type. These resources are shared by 3 processes. Okay, we have m resources of same type. Say for example, we have tape drive as resources, and we have say 25, maybe 25 tape drive or 50 tape drive of same type. These resources are shared by 3 processes A, B and C, which have peak demands of 3, 4 and 6 respectively. Okay, these 3 processes have a peak demand of 3, 4 and 6. That is process A demands 3 tape drive, process B demands 4 tape drive, and process 6 demand 6 tape drive. So for what value of m deadlock will not occur? Whether it is 7, 9, 10, 13. So process A holds 2 units of resource R. Which means the number of units of each process holds equivalent to 1 less than its maximum demand. Process A's maximum demand is 3, but it should be 1 less than. Okay, it should be 1. Similarly, process B holds 3. Actually, the demand is 4, but we need to subtract 1. So 3 units of resources are. Process C holds 5 units. Actually, the need is 6, but it has to hold 5 units of resource R. Okay, thus the maximum number of units of resource R that ensures deadlock is 2 plus 3 plus 5 is equals to 10. Maximum number of process. And then minimum number of units of resources R. Okay, that ensures no deadlock is 10 plus 1 is equals to 11. Okay, so any number of units greater than 11 will ensure no deadlock. So that option D is correct. So what is the option D? 13. So 13 resources are required. We can simply add 3 plus 4 plus and 6 respectively, but that way is see, for this kind of question it will be easily calculated, but it is not be same for all type of questions. So just go with the procedure, okay, and choose the right option. And the next question is, consider a system having m resources of same type being shared by n processes. Resources can be requested and released by process only one at a time. The system is deadlock free if and only if the sum of all maximum need is less than m plus n. M is nothing but resources plus number of process. Okay, the sum of all maximum need is less than m plus n. The sum of all maximum need is greater than m plus n. Both of above, none of this. The question is, system having m resources, tape drive, printer, okay, only tape drive because m resources of same type. that is shared by n process. It may be from P1, P2, P3 or till Pn. Resources can be requested and released by process only one at a time. If process P1 holds state drive and it has to be released only once, not frequently you need to request and get it. The system is deadlock free if and only if. Let's see. So we have derived from the above question maximum number of units of resource R that ensures deadlock is summation of xi minus n. So we already derived this max for finding maximum number of units of resource R. So thus for no deadlock occurrence, the number of units of resources R must be greater than summation of xi minus n. Okay. So that is resources should be greater than summation of xi minus n, or summation of xi should be less than n plus 1. So that the correct option is A. The sum of all maximum need should be less than resources plus process. Okay, the next problem. Consider the following snapshot of a system running n process. Process I is holding xi instance of resource R for 1 is less than equivalent to I is less than equivalent to n. Currently all instance of R are occupied. Further, for all I, process I has placed a request for an additionally yi instance while holding the xi instance it's already as. So there are exactly two processes P and Q such that yp is equals to yq is equal to 0. Which of the following can serve as a necessary condition to guarantee the system is not approaching a deadlock? Whether minimum of xp minus xq less than maximum, xp plus xq greater than equal to minimum, and minimum of xp comma xq is less than 1, and minimum xp comma xq is greater than 1. Okay, so according to the condition we have derived as, consider we have a process P1 to P1, P2, P3, Pp, Pq, Pn and hold units of x1, x2, x3, xp, xq, xn. Requested units may be y1, y2, y3 and this process is not requested, and this is also not requested, and Pn is also requested for y1. So clearly process PQ and process PP and PQ do not require any additional resources. Okay, because P1, P2, P3 already it holds x1, x2, x3 units. Additionally, it requested for y1, y2 and y3, and Pn wants yn. So they continue their execution. Okay, they continue their execution. It is because if they doesn't want any additional resource units. Okay, so after getting executed completely, they release the units allocated to them. What is the allocated units for them? XP and XQ. Okay, so these number of units get freed and it can be added. So if you add the total units that get free up is equals to XP plus XQ. So now to ensure the other process are executed without any deadlock, the total amount of units freely available, that is which is currently available, must be able to meet the requirements of some other process. So if available units could not meet the requirement of any other process, then certainly there would be a deadlock. Thus for no deadlock, the necessary condition is xp plus q is greater than is equals to minimum of yk. Okay, did you understand? See, we need to ensure that there is no deadlock when the process requires for an additional units. P1, P2, P3 already it has x1, x2, x3 and these three process also have some resources. Okay, they are running the process with the whatever the resources they have. Additionally, P1 requires for y1, P2 requires for y2 and P3 requires for y3. But these two doesn't require, it keeps executing, and after execution it will free these units. Already whatever which is held by PP and PQ, those units will be free now. Now you need to think all the process must be not in a deadlock situation. Because you need to allocate, we have a currently available are XP and XQ, right? These three units, available units will make sure there won't be any deadlock situation occurs. Okay, so if there is no deadlock, then these units must be greater than the requested unit. Okay, clear? that is what they say here. If the available units could not meet the requirement, if it is less than the requested, if see, if these two are free, and if it is less than the requested unit, then sure there will be a deadlock. But if these two are greater than the requested, then there is no deadlock. The necessary condition may be xp plus xq greater than equal to minimum yk, where k is not equal to p comma q. Okay, so here what is the option we need to go for? Second one, xp plus xq greater than equal to minimum k is not equal to p comma q and yk. Okay, right. So finally we came to the summary. So it is very important to note that above condition is just a necessary condition and not at all a sufficient condition to avoid the deadlock, and all the above four condition just ensures that system is able to proceed from the current state, and it does not guarantee that there won't be a deadlock before all the processes are finished. And the sufficient condition to avoid the deadlock could be either xp plus xq greater than equal to summation of yi, or xp plus xq greater than equivalent to maximum yk, where k is equivalent to p comma q. Okay. Okay, thank you students.